The directions say, change each of the following to fractions or mixed numbers. Hint, if the decimal expansion is terminating, we'll use a T for terminating, use place value. If the decimal is repeating, we'll use an R for repeating, use the 9 rule, or the algorithm if the repeating pattern does not begin right away. All right, I don't expect this to make sense to you just yet, but we're just going to take this in baby steps. So the first thing that we're going to do is we're just going to make sure that we know the difference between a terminating decimal and a repeating decimal. So look at this first decimal value. In this decimal value, you can see that there are 3 places, tenths, hundredths, thousandths, and it ends. There's no other number past the 5. So we would call this a terminating decimal. Number 2, negative 12.9. We have a value in the tenths place, but then there's no number afterwards. Technically, you could say, well, 12.9 is the same as 12.90, 12.900, but if there's just zeros after it, this is considered, the negative 12.9 is considered a terminating decimal, that it ends. Look at example 3. Example 3, when you look at this decimal expansion, there's a bar over the 8. If there's a line over the 8, that really means that the 8 is the part that repeats. So you could just keep writing the 8 again and again and again and again. It never ends. It just keeps on going. So since this never ends, there's always going to be another 8. 8, 8, 8, 8, 8, 8, 8. This is called a repeating decimal. It never ends. All right, example 4. Look, we have that repeat bar again, and that repeat bar says what's being repeated. So the pattern, 7, 5, 7, 5, 7, 5, 7, 5, it's being repeated. Both those numbers, that pattern's being repeated forever. So this never ends. So this is also a repeating decimal. Number 5, we have the tenths place and the hundredths place, and then it ends. So this is a terminating decimal. And then number 6, this pattern repeats, 2, 10. So it would look like this, 2, 1, 0, 2, 1, 0, 2, 1, 0 forever. Remember, the repeat bar is over the part that repeats. So this pattern is what repeats. So we call this a repeating decimal. Now, last year and in previous years, you practiced changing terminating decimals to fractions and mixed numbers. You have never taken a repeating decimal and changed it to a fraction. But I'm going to start to show you how to do that today. We're going to start very basic today. Let me show you some different numbers so you can get an idea of a pattern. So let me show you, we'll start with the ninths. 1/9, take a look at what that equals. It equals 0.11111, and that goes on forever. Take a look at 2/9. Look, 0.22222, that goes on forever. All right, 3/9. Take a look. 33333. 4/9. I hope you're starting to see the pattern. Now, the calculator, do you see the calculator just rounded? It's really 0.555555 forever, but the calculator is not going to keep filling up numbers forever, so it just does this to a certain point, so it rounds. And if the number back here was a 5 and this was a 5, the 5 would make this 5 round up to a 6. So that's why that says a 6. All right, so let's go ahead and look at some 2-number pattern examples. So let's say that you had 23 divided by 99. Look, it would show the pattern 2323232323. So this time I have 23 is the pattern, and then I put it over 2 9s instead of just 1 9. Okay, let's try it with, I don't know, 107 over 999. Take a look. 107, 107, 107, 107. So we can take this pattern that we're seeing and go back to the problems we were looking at and use that knowledge to be able to change our repeating decimals to fractions. Let's do these problems in order. So let's look first at this terminating decimal. So the first thing I'm going to do is I'm going to record the 8 in front, and then I'm going to take the 15, and since this is a terminating decimal, we're going to be using place value to change this to a fraction. So I count tenths, hundredths, thousandths, and I place 15 over 1,000. Now both 15 and 1,000 are able to be divided by 5. 15 divided by 5 is equal to 3. And let's think about 1,000 divided by 5. Well, 10 divided by 5 is 2, so 1,000 divided by 5 is 200. And that's as simple as it gets. So my final answer is 8 and 3 over 200. Right, example 2, negative 12.9. This is a terminating decimal, so we use place value. So we get negative 12 and then 9 tenths, since this is the tenths place. And 9 tenths can't be reduced, so we're finished with that problem. All right, now we're getting to this repeating decimal. So if you have a repeating decimal, we use the 9 rule, or we use the algorithm if the repeating pattern doesn't start right away. I gave you examples today where the repeating pattern starts right away to make it simple, so we can just use the 9 rule. So here's how the 9 rule works. The 9 rule is basically a shortcut. So if this pattern is one number long, there's one number in this pattern, an 8. That's the only number in that pattern. Then you place it over 1, 9. Okay, so we just wrote that repeating decimal as a fraction. Look at this one. I start by writing negative 5, and then I take the pattern. Okay, there's 2 numbers in this pattern, a 7 and a 5. So I need to place this over 2 9s. That's what I'm talking about when I say the 9 rule. Now, 75 can be divided by 3, and we can also divide 99 by 3. So I get negative 5, and 75 divided by 3 is 25. And 99 divided by 3 is 33. 25 is divisible by 5. It's equal to 5 times 5. And I can't divide 33 by 5. So I know this is as simple as possible, because I wrote the prime factorization of 25, and 33 is not divisible by either of those numbers. Well, I guess technically it's really the same number, 5. All right, number 5, this is a terminating decimal. So we use place value. So this is 17 and 11 over tenths, hundredths. Remember, with the terminating decimal, you use place value. So I put 11 over 100. 11 is a prime number, and 100 is not divisible by 11, so that is reduced as it gets. And then for this last example, 210, the pattern is 3 numbers long, so I put this over 3 9s. Remember, with repeating decimals, we use the 9 rule to change it to a fraction, if the repeating pattern starts right away, which it does. Now, 21 I know is divisible by 3. So 210 divided by 3 gives me 70. And 999 divided by 3 gives me 333. Now I'm going to complete the prime factorization of 70 to make sure I can't divide this by anything, divide both by anything else. I want to make sure that it is reduced fully. All right, so this doesn't break down any further. So 70 breaks down into 7 times 5 times 2. So all I have to do is check. Can 333 be divided by 2? Well, no, it doesn't. It's not an even number. It doesn't end in an even number. 333 is not divisible by 5. This final number is not 0 or 5, so I can't divide it by 5. Now 333 divided by 7. I have to try this and see. 7 goes into 33. Well, 7 times 4 is 28. 7 times 5 would be too much. And then bring down the 3. 7 goes into 53 7 times. 7 times 7 is 49. (13 minus 9 is 4. 4 minus 4 is 0. And then I'd have to add a decimal. If I'm adding a decimal and a 0, that means that it's not 333 is not evenly divisible by 7 without a remainder. There's going to be a remainder if I have a decimal that I'm adding. So I know that this is reduced as possible. So this is 70 over 333. Now I know that a mistake that I make sometimes is dropping a negative, so I'm going to go back and check. Okay, positive, remain positive, good. Okay, these were positive, that's a negative, that's a positive, that's a negative, that's positive. Okay, I didn't drop any of my negative signs, so I checked my work. Please use this video so that you can complete those examples where you change terminating and repeating decimals to fractions.